I'll be doing functional equations today. You should have a set of notes which has been handed out to you by this lovely gentleman in front here. Please take a bow. The notes will be roughly related to what I'll be doing today, but not exactly following that. So, what is a functional equation? Who knows what a functional equation is? Two people, no, three people, no, four. Okay, this is getting too much now. But maybe there's some who don't know what a functional equation, but I'll go very fast through the first, like what a functional equation is. So, what is a functional equation? Okay, first of all, hopefully you know what a function is. So a function is some mapping. It doesn't matter what letter we call it. We can call it different things. But it has some name. It's some mapping that goes from one set to another set. And what it does is it takes for each element in the first set, that outputs a specific element in the second set. So those sets could be finite sets, like this could be the set of numbers 1, 2, and 3, and that could be another finite set, or they could be infinite, as long as it's a mapping from one set to another set. Okay. When we have functional equations in Olympiads, most of the time it's find all functions that satisfy some property. That's usually what it looks like, and that property is usually an equation. That's why they call it functional equations. Find all functions that satisfy this equation. Sometimes when you get to the harder stuff, then they'll have more exotic conditions, or sometimes they don't even ask you to find all functions. Sometimes they just ask you to find one. Those are usually the harder ones. Okay. So a function, for each element here, it associates to that another element in here. So your x gets mapped to f of x. Usually in Olympiads, your input set and your output set would either be the set of integers or positive integers or real numbers, sometimes rational numbers, or some more exotic set. So the first part, which is your set of input values, is called the domain. And this, your output values, is called the codomain. Oh, sorry, that I forgot to introduce someone. This over here is Mr. Moorman. Everyone say hi, Danny. He'll be recording the lecture, but he'll be recording me, not you. Unless you want to be recorded, you can just like come over here. Please don't do that. Yeah, but feel free to ask questions and interrupt me at any point, or yeah. Well, the way I usually do lectures is if you ask me a question, you get something in return. I don't have them with me right now, but I'll like bring a bag of chocolates or something tomorrow. So there are rewards to asking questions. There are also rewards to sitting in the front row. I just made that up now. So maybe you'll get some chocolates tomorrow. Okay, so the domain is where your input values are allowed to be in, and your codomain is what the output values are. So what effects does this have on a functional equation? Well, if your domain is, let's say you have a function from the integers to the real numbers. That's a reasonable choice of domain and codomain. If your function f is like that, it doesn't make sense to talk about f of 3 over 2. Like, just this doesn't make sense. Because 3 over 2 is not an integer. You're only allowed to put integers into it. And then you'll get out a real number. You also can't talk about f of root 2. Because anyone who doesn't know, root 2 is not rational. Should I prove it?
Yeah.
No. You can prove it if you want to. In your spare time. Okay. So you can only put in values into the function that are in your domain. The codomain tells you, okay, once you put in the value, this is the kind of values you can get out. So here, if f goes from integers to real numbers, f of 2 or negative 2. Negative 2 is an integer. F of negative 2 can be any real number, unless we have some other condition afterwards. But if we are told that f goes from the integers to, let's say, the natural numbers, then we know that f of negative 2 has to be a natural number. Okay. So let's do some examples just to illustrate how you actually use what the codomain and the domain are for functional. So let's say you're in an Olympiad exam test or something, and the question is something like this. So find all functions f from integers to, let's say, non-negative integers such that f of x plus y is f of x plus f of y. Okay. Just this notation. There's different notations that are used around the world for integers is pretty much standard, but when they're talking about non-negative integers or positive integers, which are two different things, sometimes like this notation n, okay, for you guys, does n include 0 or not, this set?
Yeah.
Some people say no. Does anyone say yes? In some countries, n includes 0, and in some countries it doesn't. So that's why, like in IMO, they would rather use a notation like this that explicitly says z greater than or equal to 0. Also, another strange thing, in French, if you say a number is positive, it includes 0. Although in English, positive means not like strictly greater than 0. Anyway, so you want to find all functions which satisfy that equation. Any ideas what the solutions are to this? I mean, that's the first step to solving any functional. First step to solving a functional is? No, before you substitute something. Yes, you guess what the solution is. You look at the equation, you think, okay, what sort of function would satisfy an equation like this? Sometimes your first guess happens to be all of it. Sometimes as you work with it, you find, oh, there are other things that work as well. But yeah, first step is to guess. What sort of function satisfies an equation like this? Absolute value does not. No. Because absolute value of negative 2 plus the absolute value of 1 is not the same as absolute value of negative 2 plus 1. But almost. Any other hands? Yeah?
F of x equals to x.
Okay, f of x equals x works. Are there any more?
F of x equals a constant times x.
Yep, so constant times x also works for this sort of equation. You can keep guessing, but that's the only ones. In general, it's only a constant times x that satisfies this equation. More conditions on that, but we can get to that later. Okay, so we can guess that f should be a constant times x. But there's an issue with the codomain over here. What does this codomain tell us? It's integers that are greater than or equal to 0, which means your f of x is always greater than or equal to 0, even if your x is negative or your x is positive. Okay, so how can we use this? So first of all, we can find out what f of 0 is. If we put x and y both equal to 0 there, so x and y. By the way, it's probably a good idea to develop your own notation for how you substitute things into variables when you do functionals. I usually do like the variable x and y and then a back arrow to indicate what I'm putting into that. Anyway, so if we put x and y both equal to 0, we get f of 0 is f of 0 plus f of 0, which is 2f of 0. And that tells us that f of 0 is 0. Okay. And whenever you have a new piece of information, when you're solving a functional, you have a new piece of information, you always try to feed it back into the functional. So functionals, you start with your original equation, you take a special case of it, you get some, f of 0 equals 0, you put it back into it to get more information, you get something else again, you get another equation, you put it back into the original, and you keep on feeding it back until you actually find out what all the possible solutions are. Most of the time it works like that. So we've got our f of 0 equals 0. How can we feed it back into the original equation? Yep?
You say x is x and y is 0 and substitute back in.
Okay, so let's see what happens if we do that. So we put x, we're going to put in x, and y we're going to put in 0. What we get is f of, so x plus 0 will just be x. We'll have f of x and f of 0. F of 0 is 0, so that's just f of x. So in this case, it doesn't give us anything, because it just gives us f of x equals f of x. Okay, is there another way that we can put f of 0 back into, yeah?
Let y be negative x.
Yes, we let y be negative x because we want to make this a 0, so that this is f of 0. So, put y to be negative x, and we'll have, on the left-hand side, we'll have f of 0, and on the other side, we'll have f of x plus f of negative x. Now we're basically done, if you can see why. Why are we basically done? Yeah?
So the codomain is all the things have to be greater than or equal to 0. You got two things that are greater than or equal to 0, add them together, you get 0. They must both be 0.
Exactly what he said. So you got 0 equals to adding these two things. Each of these is non-negative because the codomain is non-negative integers. So that's greater than or equal to 0 plus 0, which is 0. But we know that there's equality in this inequality, and the only way that can happen is if both of these are, in fact, 0. So that gives us that f of x and f of negative x are both 0. And for which values of x is this true? We haven't put any conditions on what x can be, so this is true for all x in your domain, which is the integers. So you actually get that the only solution is when f of x is identically 0. So that's an example where you use the codomain in order to restrict, where you don't just use the functional equation itself, but you actually use what the values of the codomain are in order to determine what the function is. Good. Any questions before? I think I'll write down one more example that you can do at home. And then I'll move on to how to use the domain. So let's find all functions f from the reals to the interval from -1/2 to 1/2, such that f of x, y is f of x times f of y. Okay, so that's if you want to practice, that's some homework for you. To guess, what sort of solution would work for this? F of x, y equals f of x, f of y. Yeah?
Some kind of like a monomial, like x is to the power of something.
Yeah, x to the power of something generally works for that. Good. So that's how you use the domain. Okay, now how do we use, no sorry, that was how to use the codomain. How do we use the domain? Well, most of your functionals that you would get would either be a function from the reals to some other set, or there would be functions from the integers or the natural numbers to some other set. So usually, not always the case, but usually the real ones, it's more just algebraic manipulation, substituting things into each other until you get what f has to be. Whereas the integers and natural numbers are more likely to involve some sort of induction. So if you have a function from integers or naturals, chances are you're going to use induction. So to do induction, you would probably need, whoops, there's an I missing over there. So to do induction, you want to find what the possible values of f are. You would probably start with some small values, f of 0, f of 1, try to get what those are, and then, yeah, by induction prove the formula for the rest of the integers. I don't know, should I self-promote on this sort of, like should I give you one of my own problems? I shouldn't, no, I'm not going to. Okay, but I can use this as an introduction for the Cauchy equation. You've actually seen it before. So let's say you've got a function from the integers to the reals where f of m plus n is f of m plus f of n. This little thing is called the Cauchy equation. Okay. And it is called that because under specific set of circumstances, as we've guessed before, the solutions look like a constant times, well, your input value. So f of n would be a constant times n. And under a certain set of conditions, this is generally true. One of those conditions is if your domain is the integers. Then you can just prove by induction that f of n is always a constant times n. For example, okay, how do we do this? We want that f of n should be some constant times n. What would the value of this constant be in terms of the function itself? Can we write, if this is true, f of n is Cn, yeah?
It would be f of 1.
Yes, it would be f of 1, because if we put n equals 1 in here, we would have C equal to f of 1. So what we actually want to prove is that f of n is always f of 1 times n. That's what we want to prove using this. Okay, so let's do this by induction. What's our starting or our base value? You know how induction works, right? Everyone knows? Okay, anyone not know how induction works? Then I can give a quick explanation. Okay, so induction is generally when you want to prove a particular statement that depends on a natural number parameter. For example, this statement over here, this is actually not just one statement, it's infinitely many statements depending on what the value of your natural number is. So, for example, this could be f of 0 equals f of 1 times 0. It could also, that's if n equals 0. If n equals 1, it would be f of 1 equals f of 1 times 1. If n equals 2, it's f of 2 equals f of 1 times 2, and so on. So you actually have infinitely many statements depending on some natural number or integer parameter. And induction is a method or a strategy of proving these infinitely many statements. The way it works is that you would prove your statement that you want to prove for some base value, for usually at some small value of n. So for example, we could prove that this is true when n equals 0 or when n equals 1. So first start, prove for your base case. Sometimes there's more than one base case, usually only one. So for example, when n equals 1, that is obviously true, because f of 1 is f of 1 times 1. N equals 0, that's the same as saying that f of 0 is equal to 0. We did that before I rubbed it off with this equation. You put one of them, you put m and n both equal to 0, you get f of 0 equals 0. So those are your base cases. And then the second part is usually the harder part. You prove that if your statement is true for n, for some value of n, then it is also true for n plus 1. So this is more general case. So you're proving that if it's true for 5, then it's true for 6. And if it's true for 6, then it's true for 7. If it's true for 7, then it's true for 8. And in this way, you cover all the natural numbers. And that's how induction works. Okay, so we're going to prove this by induction. We've proven that it's true when n equals 0 and n equals 1. Now, we're assuming that it's true for some value of n. So we assume that f of n is equal to f of 1 times n. Now we want to prove the corresponding statement for n plus 1. So we want to find what f of n plus 1 is, and hopefully get to f of 1 times n plus 1. That's what we want to get to. Okay, what can we do with f of n plus 1? Using the equation, the original equation that we have. Well, we can put m equals 1 in here. Then we get f of n plus 1 is f of 1 plus f of n. That's from the original equation. Then we use our assumption. So that's f of 1 plus f of 1 times n. Now we can take out the common factor of f of 1. And we have n plus 1 as we wanted. So that finishes our induction, or does it? Does it finish our induction?
We need the function 1.
We need to.
Yeah, we need to take care of the negative values.
Yes.
Because we've only taken care of 0 and all the positive ones using this induction. So usually induction only happens in one direction, but we also need to, because the domain is the integers, we need to handle negative numbers as well. So how can we do that? Well, we know that f of 0 is equal to 0. We've done that before. So we can take our equation over here, and let's say we put m to be negative n, so that we get a 0 in there. So what we would get is 0, which is f of 0 would be equal to f of negative n plus f of n. So another way to write that is that f of negative n is negative f of n. And if n is positive, then we know what that is. That's, we've done by induction, that's negative f of 1 times n. That's if n is positive. So we have that f of a negative value is also f of 1 times negative n, that negative value. Okay, so now we did 0 and 1, all the positive numbers, and we use this to reflect back onto the negative numbers. So that's how we do by induction the Cauchy equation for integers. By the way, this condition is called a function being odd if it satisfies this reflective property. F of negative n is negative f of n. Okay, so that's the Cauchy equation on the integers. You can actually do basically the same thing, maybe a bit more steps, for the Cauchy equation on the rational numbers. Still works the same way. But you actually can't prove the Cauchy equation using this inductive approach if you want to do the Cauchy equation on the real numbers. Then you need some extra conditions in order to get f of x equals a constant times x. Okay, so that is a function, domain, codomain, and some induction and Cauchy equation. Any questions before I move on to some more stuff? No. Okay. Okay, so that's domain, codomain. Something else that you might have heard of is the range of a function. Everyone look at John. Just look at him. Okay, you've heard of the range of a function, which sometimes gets confused with a codomain, but it's not the same thing. So the codomain is the values that your function is allowed to take. So here, f is allowed to take real values. The range is all the values that it actually hits, that it actually goes on to. So, for example, the codomain, you could have a function from the natural numbers to the real numbers, where f of n, your natural number, is just n. Here, your codomain is the real numbers, but your range is all the values that the function actually takes. In this case, the range of f is the natural numbers inside the real numbers. Range is actually a special case of a more general thing, and this notation might actually take a bit of time to get used to it. So the thing called image and pre-image of a function, or image and pre-image of a set. So image works like this. If you have a function from x to y, you have a function from x to y, and you have a subset of your domain. So let's say S is some subset of your domain on the left-hand side. Then we can denote the following by f of your subset. And it's defined as follows. It's the set of all values of f of x, where x is in your subset. Perhaps to help with it visually, you have your set x, you have your codomain y, some points over here, and these get mapped to points on this side. Now your S might be the subset consisting of only these points in the lower half of x. In that case, f of s would only be the subset of the codomain consisting of all the values that come from the subset S. As a special case of this image construction, we can say, okay, what happens if our subset S of our domain is the whole space? So if S is equal to X, the full domain, then f of the whole set X is also called what? Yes, that's exactly the range of f. Okay, and together with the image of a subset of a domain, we also have something called the pre-image, or inverse image, some people call it. I'll call it pre-image. So for the image, you take the subset of the domain and you see what it gets mapped to. For the pre-image, you take a subset. Someone give me a letter. J. So a subset J of your codomain. So this time you're taking a subset of your codomain. And then the notation is F inverse of J. And the idea is that if J is this subset of your codomain, that's all the stuff in your domain which goes into that when you map it with F. So F inverse of J is all the X in your domain such that f of x is in your subset J. Oh, by the way, if anyone is having trouble reading, I can write a bit bigger. You could also move closer to the front. There's lots of space in here, as you can see. Ta-da. Okay. Okay, what happens if we look at the pre-image of the whole codomain Y? What do we get? So we want all the set of all x in your domain such that f of x is in the codomain. Yeah?
You get your domain?
Yes, you get your domain. So the pre-image of your whole codomain is always the whole domain that you started with. Let's test some other ones. What is the pre-image of the empty set? Yep. Because everything in X gets mapped to something. So if you want all the X's that don't get mapped to something, there aren't any. So you only have the empty set. And sort of related, what is the image? So that was the pre-image of the empty set. What is the image of the empty set? The set of all f values that come from the empty set. Empty set, she says. Yes, that is also the empty set. Okay, so we did domain, how to use that range, how to use that. Codomain as well, image, pre-image. Now some more useful stuff as well. It's often useful to figure out whether or not, or if you can prove that a function is injective or surjective, it can often be used later. So an injective function satisfies the following condition, is that if f of x is equal to f of y, then x is equal to y. Okay, that's what injectivity means. And surjectivity I think when I first encountered it, I found surjectivity a harder thing to prove or to write down, but it's actually not that bad. Surjectivity means that for every y in your codomain, so let's say we're dealing with f from x to y, surjectivity is for every y in your codomain, there is some x in your domain such that f of x is equal to y. Might take more time to understand what that means if this is your first time encountering it. But it basically means that the range of your function, all the values that are actually taken, happens to be your whole codomain y. So your function covers the whole codomain. It doesn't just go to a subset of it. Okay. An example of how to show that a function is injective or surjective. Let's suppose you've got the following functional equation. Okay, let's suppose that's your functional equation and you've got f from the reals to the reals. Okay, how can we prove that f is injective? It's actually pretty straightforward. We just follow the criteria of injectivity. We start with assuming that two values of f are the same, and then we prove that the input values are the same. Keep in mind, you don't have to have x and y equal to each other, because here x and y are our free variables that you have in the equation. So we could say let f of a equals f of b, and we want to prove that a is equal to b. So let f of a equals f of b. How can we get that a is equal to b? Well, one way is to put x to be equal to a and to put x equal to b in this equation over here. So we have f of a plus f of y, f of Okay. Now, because you know that f of a is equal to f of b, both of these left-hand sides are the same. So we get that both right-hand sides are the same as well. The yf of y's cancel on each side. Actually, let me just write that down first. Af of a, yf of y is equal to df of b, yf of y. And yeah, taking away yf of y on each side, f of a is equal to b, f of b. We know f of a is equal to f of b, so we can divide by that, and we get a equals b. I'm glad you guys picked that up. Thank you. Only 2 people picked that up over there. Or you picked it up and you just didn't mention. What's wrong? Please tell me your troubles. Please, what's wrong? Did I do something wrong, perhaps? Any?
Yes.
Actually, I should ask any of the teachers, did I do something wrong here? What did I do that was wrong? You're not a teacher. I'm assuming something. What am I assuming? I'm assuming that I can divide by this f of a, f of b value over here. So this is only if f of a, which is the same as f of b, is not equal to 0. So in this case, we actually don't have an injective function. We have something that's almost injective. So as long as this common value between a and b is not 0, then it's injective. But otherwise, you could have like f of 1 and f of 2 both being equal to 0. So sometimes you don't get full injectivity, sometimes you do. For example, I think if we change this as follows, if we did that instead, I think you would get like full normal injectivity. Well, almost. You would get either injectivity or the function has to be constantly equal to 0. Okay, so injectivity is usually pretty straightforward to prove. And why is it useful? Well, it's useful because sometimes you would have something like you're busy manipulating equations, substituting things into each other, and you end up with like f of something over here is equal to f of something over there. And injectivity then allows you to take away the f's and say that those two things on the inside are equal. For example, you might substitute various things, and eventually you get to f of n equals f of n. And if you happen to prove earlier that it's injective, you then get that f of n equals n. Good? Okay, so that's injectivity. Now for surjectivity, I'm going to give you another little condition. Let's suppose that that's your functional equation, and you're given that f of 0 is equal to 365. You just happen to be given that extra information as well, and now you want to prove that this function is surjective. Any ideas? Well, so we're given the value of f of 0, and like I said with the function earlier, you keep on pumping the information that you get back into the equations that you get, and you get simpler and simpler, hopefully, until you get to what the function actually is. So let's use this f of 0 equals 365 in this functional equation over here. We can do that, for example, by putting y equals 0. If we put y equals 0, on the left-hand side we get f of x plus f of 0, which is 365. On this side, well, we'll have 0 times f of x, so that goes away. And over here, we have 365x. Now, when you're doing surjectivity, it often helps to look at an equation and imagine varying the variables. So, on this side, you have f of something. That thing can change in some complicated way. You don't know but you don't know what f is. This could be some complicated thing, but it's f of something. On this side, you have 365x. As x changes, varies as a real number from negative infinity to positive infinity, which values does this take?
All of them.
Yeah, it takes all of them. 365x can take any real number value you want. So this is any real value, which means for any real value we want, we can find an appropriate x, and we'll have f of something equal to that real value. And that's exactly what surjectivity is. For any value I want in the codomain, I can find something to put inside an f. So this is f of something. I can always find f of something to be equal to whatever y value I want. And that's surjectivity. Okay, do I need to repeat that again? Or are we good? We're good. Okay, why is surjectivity useful? Well, you might work with this a little bit, and later on you get something that looks along the lines of f of x plus f of 365 equal to f of x. You might get that later on at some point in your derivation. And I notice that x doesn't appear on its own anywhere here. X always appears inside an f. So x appears inside an f there, like directly inside an f with nothing else inside it. And over here it also appears as f of x. Nothing else inside with it. So if I let's say y equals f of x, then I can write this as f of y plus f of 365 equals y. And because it's surjective, this y value can be any value I want. That's what surjectivity helps with. And then I can actually figure out what f of y is. Just take that to the other side. F of y is y minus that. So injectivity and surjectivity are both useful for getting rid of f's, but in different ways. Injectivity, if you have f on each side, you can get rid of the outside f's. surjectivity more helps you get rid of inside x. Okay, I was planning to do a lot more, but unfortunately that's basically our time for today. Do we have any last questions before you go for lunch? No? Okay, in that case it's lunchtime. There should be another lecture starting at 2 o'clock, I think? Yeah, 2 o'clock. See you later.